So what we're doing, we're talking about finding lengths, but in a specific situation. So can I have everyone in front of your book now, fresh page, put a title, finding unknown lengths. What we are looking for, so you should be used to this, statement of inquiry, generalising relationships between measurements can lead to better models and methods of calculating, finding things, finding lengths. And the questions that we're going to be looking at are, how do you find measurements of immeasurable objects? So, for instance, out on the fields, I'm going to take you out in the field at some point, I'm going to ask you to measure something. Right? So, for instance, out there, what might be something that is immeasurable? Think of anything outside?
The surface area of the field.
Well, see, I would say the surface area of the field is measurable. It's big, but it's measurable by the fact that I can get one of those wheels, measuring wheels, and just walk around the outside of the field, and it will tick off every metre, and I just record it, and then I do, because it's basically just a rectangle, yeah? So I can work it out.
The sky.
So just the fact that it's big doesn't. The sky, how would I measure? Well, the sky. Sky's not really an object, is it, to measure?
Yeah.
It's
You said that?
right. Hang on. Don't criticise. At least you came up with an idea. The basketball court is the same as the field, isn't it?
Basketball court is easier.
Basketball court would be easier, smaller.
The number of grass.
The number of blades of grass, again, actually, that's not measuring, it's counting. And I could ask you to do that. I'd be really mean if I asked you actually to count them all. I'd be ridiculous. What I could ask you to do is estimate it, but that's not what I'm talking about, an actual measurement rather than counting. So the kind of thing that I'm thinking about is the height of the rugby posts.
Oh, hi.
So what? That's the thing. It's like if I lay them down on the floor, I could measure them.
Yeah.
But because they're upright, how do I measure it?
A crane. Like, get a ladder.
Well, you don't have access to a helicopter. You don't have a ladder that is as tall as those.
I can climb. I can climb up that.
So the only way you can do it is to destroy what's there, which kind of is not. Right?
You could take like a measurement of part of it and then do like multiply.
Okay.
Yeah, actually, hiking.
So we could take. It's a good idea. We could take measurement of part of it and then multiply it. That is a really good idea. Although, how do I know how much to multiply by? To know that, I have to know how tall it is. Right. So what we've got, that is kind of on the smaller scale. But for instance, I've got a picture on the screen of a bridge, a suspension bridge, a really large one. We've been talking about this measurement from, from the bottom to the top of one of those pylons. Okay? Those sort of heights, those sort of measurements. Now we can work them out. It's a height. The only reason we say it's immeasurable is not because it's not possible to measure it, but because of the situation it's in, we would have to change that situation. But we can calculate them.
Technically, the height would shift because of the sea level, right?
Well, it depends. The height could be measured from the base where it was actually built into, and then now that wouldn't change. But yes, I do get your point. Okay?
But if you're measuring from sea level.
Yeah, if we measure it from sea level. Right. Now, trigonometry then. Trigonometry is what we're looking at. So you'll notice on the bridge there is a particular shape that I'm going to be talking about.
Triangles.
The triangle. Okay? Got that? Any particular type of triangle?
No, just triangles.
Right, what I'm actually going to be looking at, okay? I'm going to look at, this thing.
Every other type of triangle is not equilateral. Right? That is not an equilateral.
Right, what I'm going to be looking at is I'm going to take this length here, okay? So I'm going to go from the road surface just to the top of the pylon there, and then I'm going to take another line, which will come on computer. Right, so I'm just going to have a long line like that. So that can be the road surface. My computer is messing. Alright, got that? Now what links the pylon with the road surface?
The wires.
The wires, the cables. Okay? So, if I were to model this situation, now what I am doing here is I am ignoring one important aspect of those cables. Right? The bit I'm ignoring is the fact that actually there will be some form of sag in those cables. They won't be perfectly taut. But in this situation, I'm going to imagine I have a perfect right angle triangle. Also, you'll notice the bridge has a curve in it. So part of this, we're simplifying. We're creating a model at the moment, but it is a simplified model. But can you see that we have a right angle triangle?
That's what that's.
Yeah? So here's a right angle triangle. So here's the right angle on that point there. That would be where the right angle is. So it's not eclipsed. Alright? Now, what you'll also notice is there are lots of cables, right? So if I drew another cable, I'm going to draw it parallel to the other cable. So there's two different cables. Does that make sense? Alright. There's lots of them there, they're all running out. But what I want to look at is one important aspect of trigonometry, which is the cable with the road creates an angle. Okay? So that symbol I've just written is like that, and it's called theta. It's a Greek letter. Okay, Greek letter. Looks like an O with a line through the middle of it. Okay? Now, if I do that, so I've got the pylon here, and I've got the road, I've got one cable. If I take the longer cable, this angle here is actually the same angle. Got that? Okay. And what we are doing is we are looking at the relationship between the lengths of like the cable and the road and the pylon with those angles. And we're going to, the angle is quite easy to measure because it's down on the road length. Okay? So we're looking at the relationships between the angles and the lengths. Got that? Okay. So, someone back in the day, years and years and years, hundreds of years ago probably, did a bit of research, okay, with their triangles. And they found certain things out. They found that if I take those cables, right, at those angles, and I create triangles, right, they found there was a relationship between the ratios of different lengths. But to be able to write these down, I've got to label the sides. So it's a right angle triangle. Do you know what the longest side of a right angle triangle is called? Begins with H.
Hypotenuse.
Hypotenuse. So we have the hypotenuse. Okay? We have a hypotenuse. This side down here, because I have my angle measured here, and we need to talk about this later, this side is called the adjacent side. It's all on the board in front of you. Okay? So those of you that haven't spotted that, alright?
You know you saw it.
And up here is called the
Opposite.
opposite.
I love that really? That does opposite come here. Yeah.
Right. Now, what you need, this is very important for trigonometry. You need to be able to identify the hypotenuse, the opposite, and the adjacent sides correctly. If you don't get them done correctly, there'll be a problem. Okay? So, first of all, how would you remember what the hypotenuse was?
High.
Okay, it's higher up, but what if I change the way a triangle is rotated around the page?
It's not
The longest part.
Oh, so the longest part. Okay? A lot of people say they remember it because it's the longest part. How could I remember the opposite and adjacent?
It's a right angle.
The opposite is opposite.
The right angle is the angle, the opposite is a side length. So in this case, the opposite side is this side, that's called the opposite. Okay? The adjacent side of the bigger triangle,
It's
all that
longer.
way, is adjacent. Okay? Now it's not always going to be longer. Not always going to be longer. Okay? Now, what I would like you to do, because some of you are just sat there at the moment, I don't know how focused. I'd like you to write that down and then try and write down a way that you could remember. Now, before I do it, I'm just going to say to you this. If I had a different triangle, sorry, okay, if I have a different triangle like this, let's say I've got a higher stanchion and I've not measured so far, I've actually got a bigger angle here. This side is still the hypotenuse. This side is still the adjacent. And this side is still the opposite.
So it's always.
So we can't say the opposite is shorter or longer.
It's the opposite is always on the left.
No, but look, on the board it says.
What if I redrew my triangle like this?
It's always the base. What? So
Oh, the
so that's
opposite's
the-
always. Oh, it's always
That's the
opposite
hypotenuse.
It's always the opposite
of the angle.
This side is the opposite. This side is the adjacent. Just to make you think one more thing, if I take the same looking triangle as that one, but this time I look at this angle, this side is still the hypotenuse, this side is the,
adjacent.
no,
Opposite.
Oh,
This-
it's opposite.
that side is the opposite,
How you are not in these two.
and this is the adjacent. So what I want you to do, in your notes, I want you to draw those triangles out,
All of them?
all of it, and I want you to write down yourself, in your own words, how would you remember how to identify the opposite and the adjacent and the hypotenuse? I've not written on the board, I would expect more in your notes.